TA. Hello, this is 637. I'm Charles Bouman, and we're going to be finishing up on the MRI material this lecture. Let me just start by saying it's very important that you stay up to date with the labs. If you fall behind on the labs, history says that once you fall behind, there is no catching up. And I expect everybody to do the labs, okay? It's not optional, and I won't look out on it kindly, okay, if you don't do them. And by the way, we have lots of resources, okay? We got 2 TAs, and we got like a roving help person too, as far as I can tell. So, and then we have me, okay? So, well, I don't know. I think that's positive, but okay. Well, but here's lots of good resources. There's no excuse for not getting this in, okay? So, so do the labs, okay? Are there any questions? Okay. So I'll get started with the MRI material again. So let me just quickly review the upshot of all this. Let me go over the whole thing really quickly, just to refresh your memory on how this whole thing works. So we talked about the MRI scanner. Okay, so the scanner has a coil which produces a sort of a background level of magnetic field that's very intense. And when you talk about a CT scanner, usually they'll say it's like a 1.5 T or whatever, 3T. Well, the T stands for Tesla. Okay, so it's like they're saying, well, what is the nominal level of magnetic field in the center of the bore? And so a stronger magnetic field will produce a stronger signal, which means you get usually better signal-to-noise ratio, or you can use it to do faster scanning. But in any case, you have a strong magnetic field formed by a superconducting magnet, and they have linear gradient coils. So the gradient coils produce a magnetic field which is spatially varying, and it's a linear spatial gradient, hopefully. So it's proportional to position. So if there's 3 separate inputs. By the way, remember the magnetic field is a vector quantity, but we're going to treat it as a scalar because we're assuming that the magnetic field direction is constant. And it's only the amplitude that's changing. Okay, so so you have 3 inputs to the gradient coils. One input is is in the x gradient, another in the y gradient, and the third is in the z gradient, right? So you can imagine this is like a plane that you're tilting, okay? But it's not a plane because it's 3 dimensions, but if it was 2 dimensions, you could imagine it as a surface where the amplitude was the magnitude of the gradient. It can vary linearly by tilting it in x or y, or you can do an arbitrary tilt. So you have 3 inputs. Now, initially what happens is that you first put no gradient in x and y and just have a gradient in z. And then you use an RF pulse, and the frequency of the RF pulse is selected so that it's tuned to a particular slice. So what happens is that at different z positions, the resonant frequency will vary slightly because of the fact that there's a slope to the magnetic field. So where the magnetic field is larger, the resonant frequency will be higher, and where it's lower, the resonant frequency will be smaller. So there's going to be a modulated sync. So the sync function makes the frequency response of the pulse a square bandpass response. Okay, so it's with a center frequency at some frequency, say nominally 63 megahertz, but the center frequency will shift slightly depending upon where you want to select the slice. And the length of the sync will determine what the thickness of the slice is. Okay? So once you've selected the slice, then all the protons in that slice are resonating at the same frequency. Now, if you shift the magnetic field amplitude, if you change the magnetic field amplitude, that frequency of resonance will shift. It's like modulating the frequency of in FM. So, in FM radio you have a voltage-controlled oscillator, is a VCO, and you change the input voltage and it changes the frequency, right? So you're modulating the frequency, and as you modulate the frequency up and down, that's how when you send an FM signal, like on FM radio, you have somebody's voice, and the voice controls the frequency of the oscillator, and as the frequency goes up and down, you demodulate it and you get the person's voice back, okay? So it's the same concept here, where you modulate the frequency in the slice by changing the magnetic field. So a changing magnetic field produces a different resonant frequency, so the frequency instantaneously shifts up and down, okay? Now what happens, so to do that now, you take this slice and you're going to vary the gradient in the x and the y axes so that at each voxel you'll get a different frequency. So it's like FM radio. Each one you have a different frequency, and you're going to demodulate that sort of at a different frequency. The way you'll demodulate it really in the end is with an FFT, which is how you do reconstruction. Okay, so for this particular voxel, here we don't have Z anymore. Well, we didn't have Z before because I had an error in the notes, but there's not supposed to be a Z here because now we're restricting ourselves to just that one slice. And at this XY position now, we don't change the gradient in Z. We leave that alone, okay? And now we just shift the gradient in X and Y. And by shifting the gradient X and Y, we'll change the magnetic field strength at this point and thereby change the frequency of oscillation, okay? So we're going to write down the received signal as the product of two things: f of xy, which is the actual the amplitude of the signal coming from the voxel. So if the voxel has a lot of protons in it, then there's going to be a strong amplitude, and if it's a few, it'll be a little amplitude. So that's the basic contrast mechanism that we use to actually see something. So f of xy is the thing we really want to image. Okay, it represents the density of protons, say, in that voxel. It turns out the issue of how you control the contrast mechanism is a very important one. In fact, it's probably the thing that most MR people are most concerned about. They take the reconstruction for granted, and there's so-called T1 weighting and T2 weighting and T2 star weighting and all these complicated things. But I'm sweeping that all under the rug, and we're just assuming that the only thing here is that we have this function f of xy, which is what we want to image, and it's the amplitude of the response from that voxel. Okay, so now times e to the j phi, and that contains the phase and the frequency modulation. So now we're going to change the frequency modulation by changing the gradients, because when we change the gradients, the actual magnetic field at that voxel will change, unless the voxel is right at the center of the coordinate system. If it's right at the center of the coordinate system, then its frequency will be independent of the gradient, right? But if it's anywhere but there, then as we shift the gradients, the magnetic field will shift, and the frequency of oscillation of that signal will shift, right? So then what happens is you can write the equations down. The derivative of the phase is equal to the instantaneous frequency. And the instantaneous frequency is going to be equal to L times the magnetic field at that voxel. You plug in these expressions, and you get this expression. So that the instantaneous frequency is going to be the ambient magnetic field strength m0, so the 3 Tesla or 1.5 Tesla times L. So that's the 63 megahertz. This term also really should include the offset in magnetic field due to the fact that you're using a Z gradient, okay? Now, then you're going to have a gradient in X, and you're going to have a gradient in Y, okay? And so now Kx and Ky are given by these two expressions. Kx is going to be equal to the gradient in it's the integral in time of the gradient in along x. Okay. Let's see. So this is the instantaneous frequency, right? So, hold on for just a second. So, hold on, I'm trying to, oh, okay, so, right. So, hold on, okay, so, I got to stop saying so. Okay, hold on, let me see. So we have the gradient of the integral, okay, I want to make sure I understand this myself. Oh, okay. Oh, okay, so this term here, kx of t, let's look at that term. This is the instantaneous frequency. Oh, this is the, okay, this is the, oh, I'm sorry, this is the phase, okay? So the phase is going to be the is in the nominal frequency times t plus x times k of t, where k is the integral of this expression. Okay, so why is it the integral? So if you have a gradient field, so x times g of x of t, this is the additional magnetic field due to the gradient. So this is like a small shift. This whole thing here, you can think of it as like a delta in frequency. It's a small shift in frequency, only it's in units of radians. So I should multiply this by 2 pi, okay? So the phase is going to be the integral of the shift in frequency. So if I integrate this expression with time, then I get the change in the phase, because the phase is the integral of the frequency. So I get that the integral of this expression here is the change in the phase, kx of t, and that multiplies by x, because I can take the x out of the integral. So if you look at this phase term, the phase is, first of all, got a term associated with the integral of, the product of time and the center frequency. So if you take phi of t minus omega 0 t, you get that it's x times k of t plus y of k of y of t. So the difference in the phase shift, this is the difference between what you'd expect the phase to be just because it's on a carrier and what the actual phase is. So this phase shift is linear in x times k of x, and linear in y times k of y. And the k of x and the k of y are the integrals of the gradient with time. Well, when you plug that in, you get this. So you have f of xy times e to the j, these terms are here, x times k of x and y times k of y. And now you have to integrate over space. And when you integrate over space, this expression looks like a two-dimensional Fourier transform. So the received signal r of t is the value of the 2D Fourier transform evaluated at minus k of x and minus k of y times the carrier. So if you demodulate the signal, you take r of t and you multiply it by e to the minus j omega t. That's demodulation of the signal. What you get out is f at minus k of x of t and minus ky of t. So when you demodulate the signal, you're measuring the 2D Fourier transform of the object at this position in Kspace. So the way you actually do this is you have a receiver, you demodulate the received signal into what's called in-phase and quadrature. So you get the real and imaginary part of the demodulated signal. And that demodulated signal you sample and you store as a complex number, and you calculate at what position in frequency space that was. You then take all the values, you align them up in a 2D grid, and you take the inverse 2D FFT. So that's what this shows here. Now, so it looks like this. You start off at 0. Then by applying an x gradient, or say here if you applied a negative x gradient and a positive y gradient, if you apply a small gradient for a small amount of time, you'll shift the frequency. So basically what happens is that, okay, so if you apply a small voltage, the other thing here that happens is that gradient is proportional to the current, but the current is the integral of the voltage. And the voltage is the thing you actually control on the coil. So when you apply a small pulse of voltage, if you apply a small pulse of voltage like this, okay, so this is V of t, then what ends up happening is if you look at I of t, the current in the coil, what will happen is that you'll get a behavior like this. This will be 0 current. You start off at 0 current. This is 0 voltage. And when you apply that pulse, the integral of the pulse is the current. So this and the current is proportional to the gradient. So G of t will also look the same. And when there's a gradient here, the gradient then creates a magnetic field offset that increases the frequency in those voxels. So the increased frequency makes the phase increase linearly. So what will end up happening in this case is that if you looked at kx, k of t, it's the integral of this. So I guess the integral of this is something like this. It just keeps going linearly. So this is like the acceleration, this is like the velocity, and that's like the position. So if you want to go from here to here in Kspace, what you need to do is put a negative pulse in Kx and a positive pulse in Ky, and then you'll first drift over to here. When you get there, you have to apply the brakes and stop, okay? That part of the pulse sequence is a little complicated, so we'll start right there and think about what it is there, okay? So here, what the first thing you do is you apply a pulse in Kx that's positive. That kind of gets you moving in this direction at constant velocity. You drift along here, and you put a pulse in Kx that's negative, and you stop it. Then you put a pulse in Ky that's negative, and it slows you down, and then you put a pulse in Ky that's positive, and it stops right there. And then you continue this in raster order. All the time you're collecting the demodulated data and storing it, and then you do a 2D FFT to form the image. So here's the pulse. This is what the pulse sequence typically looks like. So the voltage here on Kx, you initially have a positive pulse, right? That gets you started moving to the right, and then you have a negative pulse to stop. Then you have a quick negative pulse on Y and a positive pulse. These have to be symmetric. If they're not symmetric, then you'll continue drifting along in Y, right? So in other words, you have to apply just as much brakes as you do acceleration, so they cancel. So this thing will cause you to shift down a little bit, and then you put a negative pulse so that you go backwards, and then this stops you over here, right? So this is like, I guess that's A. So this point here is A, right? And then this is B. That's right here. That's B. And then this is C. And C would be right here. And this is D. And D would be right there, okay? And then this is E. And E would be right here. Okay? And then, so then the other thing that's important to know is, well, how finely do I have to space these scans in Kspace? So by the way, these units here, this thing here has units, right? the units here are going to be, the units here are radians per centimeter, or say millimeter. We'll say centimeter. They're radians per unit distance, or radians per millimeter. So how closely do you, there's two questions you need to ask. So these things have units, okay? They're not just 3, right? Because the physical world has units, right? I mean, a person has a particular dimension, right? So if you measure a person in centimeters, so let's say a person is so 10 centimeters is I should be able to. It's 2.54 centimeters per inch. Of course, I can only think in inches. It's my so you guys, probably a lot of you think in centimeters, right? So let me see. 2.54. So that's about 2.5. So that's 4 centimeters is 10 inches, I guess. Yeah. Excuse me. No. Yeah. 4 inches is 10 centimeters, right? Okay, so that's about 4 inches. Oh, so 10 centimeters. 30 centimeters is about a foot.
That's
the way correct. We know that
yeah.
because that's the 1 nanosecond, right? So, okay, so 30 centimeters. So let's say 60 centimeters, okay? So a person is 60 centimeters wide. And let's say they're, 30 centimeters thick. Okay, so if you want to image that, right, and let's say you want to get 0.1 centimeters, 1 millimeter resolution. Oh, centimeters, right? So how do I pick the spacing here? Any thoughts? So what should this dimension be here? That's in kx. That's kind of the bandwidth of your image, right? In spatial frequency. That's 0. So what's the maximum spatial frequency you need? So if you have, well, we haven't actually gotten to Nyquist yet, so I guess I'm jumping ahead a little bit. But I feel it's not on an unreasonable level of jumping ahead, and it's useful. Okay, so maybe the easier thing to do is first this. Okay, if the object has, no, I guess neither is easier. Okay, so if I have a signal, we're going to talk about this later in Nyquist sampling, right? If I have a signal and this is 0 frequency, right? And let's say it's a real valued signal, so its frequencies look like that, right? And that's the maximum frequency, f sub c, for f sub cutoff, okay? And then that associates with some kind of time signal, right? Right. So if I want to sample this signal that has a maximum frequency of f sub c, how fast do I have to sample this signal in time? So this is x of f, and this is x of t. You have to sample it at least, so t, the sampling period, has to be equal to 1 over 2f of c. So that's the sampling period. The sampling frequency, f of s, is equal to 1 over t of s okay, that's got to be equal to 2f of c. So you have to sample at twice the highest frequency. This is called the Nyquist criteria. Okay, we'll talk about that later. But intuitively, if you have higher frequencies, you have to sample at a higher rate. And the fact that it just happens to be twice, well, that's easy to remember, because if you look at a sine wave, okay, so let's say this sine wave has frequency f sub c, right? If you sample it at the sampling frequency, if you sampled it at the highest, okay, so let's say this was, so t here, the period here is t, and t is equal to 1 over f sub c, all right? So if you sampled at the cutoff frequency, so if your sampling period or your sampling frequency was equal to the highest frequency, your samples would be all at 0. And you'd say there was nothing there, right? So that's not high enough. If you sample at twice the highest frequency, they're still actually all at 0. Okay? So you actually have to sample just a little higher than that. And that theoretically allows you to reconstruct the signal. Okay? So if you sample at just the Nyquist rate, so actually this isn't quite true. It's got to be greater than. Okay? But okay, so if you want to preserve a resolution of 0.1 centimeters per voxel, okay, then the highest frequency is got to be on the order of 1 over that, actually divided by 2, right? But so take this as to be f sub s. No, this is t sub s, right? So that means the highest frequency you need to be able to maintain is going to be 2 pi over t sub s times 2. So that's going to be equal to pi over t sub s, which is 0.1, and that's going to be equal to 10 pi. So in this direction, you need this to be 10 pi radians per centimeters. If you want to be able to, actually, that would be the minimum. In practice, you're going to need more than that, right? And same thing in this dimension. This is also minus 10 pi, and this is 10 pi, right? So that answers the question of how big the area has to be. So notice, a smaller voxel, the smaller the voxels are, the bigger this region has to be. It's a little counterintuitive. And it's a perfect example of this same underlying phenomena that shows up a lot. Okay, now how do I determine what the spacing is between these lines? And by the way, there's actually another factor, because in a real physical system, you can't make a continuous measurement. You have to sample with an A-to-D converter, so you have to figure out how rapidly you have to sample this. So in other words, there are actually discrete samples in time along here, all right? So you have to also figure out how close those have to be too. But let's not worry about them now. We'll just pick this spacing. So what's this spacing supposed to be? So if I make that smaller, what's going to change? So the voxel here, the sampling of the voxels here, so this was 0.1, right? The voxel, putting these voxels closer together have the effect of needing a larger window in frequency. Smaller in space is larger in frequency, right? Smaller in time is larger in frequency. So if I want to make, now for here I have to figure out what the spacing is between these small things. If I put these things closer together in frequency, what does that tell you about what's something that's going to happen in time or space? Excuse me? It's going to get larger, okay? So something here, when it gets smaller, has got to get bigger here, okay? Now, what is that thing going to be? The reason I'm doing this, by the way, is it's very counterintuitive, okay? So it's the thing that if you learn here in this class, you will then know for the rest of your lives and be very valuable. Because you'll be like a Marine. You'll be, what is it? The few, the proud, the signal processors, okay? Okay. So let's see. So as the voxels get closer here in space, the window gets larger in frequency, okay? There's a dual relationship. I want you to kind of guess it. We're going to learn it again, okay? But I want you to kind of guess it because it's such an important thing. It comes up a lot. So sampling, let me write this down. This is so important. Sampling in space, okay? When that goes up, right? When the sampling in space goes up, so not the sampling frequency, the sampling distance okay? Or maybe let me rewrite this. When the sample spacing goes up, okay? So this is in space, and this is in frequency. Okay? When the sample spacing goes up, then the bandwidth goes down, because they got to go in opposite directions. So when the sample spacing goes up, when the samples get further apart in space, the amount of bandwidth you need to represent that goes down. When the sample spacing goes down, then the bandwidth goes up, right? So if the samples get closer together in space, then the bandwidth goes up, okay? Now, as the sample in frequency if the sample spacing goes up here, what changes here is the field of view. Goes down. And as the sample spacing goes down, the field of view goes up. So, as the sample spacing and frequency becomes finer, you can represent a larger field of view. So, this spacing of samples and frequency is going to relate to the field of view of the object. So, here the field of view is 30 centimeters. If I need a larger field of view, so if the person gets larger, right? I need a larger field of view. Then what I need to do is put these samples closer together. So this is where there's no free lunch, okay? Because you'd say, well, I have a certain bandwidth I need in order to achieve a certain resolution. This would be like if you want a higher resolution telescope, you need a larger aperture to the lens, because the lens is in the Fourier transform domain. So a larger lens allows for higher resolution, right? More bandwidth and frequency gives you more resolution in space. So a bigger bandwidth and frequency means that you can have finer detail in space. But frequency and space are dual quantities. The Fourier transform has a duality property. If you take the Fourier transform twice, you're back in space again, okay? Just with a space reversal, okay? So sampling here corresponds to field of view there. So if that weren't true, you could cheat, because you could say, okay, I'll just scan like the outside, and I'll be done. I don't need to take any samples on the inside. Well, if you do that, sure, you'll get the highest frequencies, but you're missing all that stuff in between. So how much of that stuff in between would you need? Well, the amount of that you need depends upon the field of view here. And if you need a 30 centimeter field of view here, then you need 1 over 30. You need to take 1/2 of 1 over 30 centimeters. So this distance here then has to be 1 over 60 centimeters. And that's in, times 2 pi, because this is in radians. So that's the spacing. If you exceed that spacing, if you make the spacing too large, when you go to do the reconstruction, you know what it'll look like? You'll get aliasing. So let's say that this is what the person should look like. So that's what the person should look, right? If you sample too coarsely, you'll get overlap, and it'll look like this. You'll get the primary image, and then you'll get a secondary version. Let's say you undersampled by a factor of 2, you'll get a secondary version of the image overlaid on it. And you'll get one down here too. So it'll be a confused mess. It'll be like the person was being wrapped around themselves. Okay? That's actually that's called wraparound sometimes. So in order to avoid this is called aliasing. In order to avoid aliasing, you need to make the spacing here fine enough. By making this spacing finer, you make the field of view larger. So it's always the case that in one domain you make something small, and in the other domain you make it large. All right? Yeah, and that's important because otherwise this is what limits the speed of the scan, because you're required to go back and forth this many times and to take a certain number of samples. And the spacing between these samples in this dimension needs to be what? Well, this would be 2 pi over, the person is, how wide did I decide? The person's 60 centimeters wide and 30 centimeters thick. So this would be 1 over 120. So the samples have to be finer in this dimension than they do in this, because the person is wider than they are thick. Of course, when you really do this, you have to be a little bit conservative. You tend to sample a little bit higher rate than would be the minimum necessary to make sure you don't have any problems. And plus, maybe you don't know precisely how big the person is, so you have to, be a little bit, oversample a little bit to make sure you don't have any problems. And even if you oversample, it's not the worst thing, because you get a little better signal to noise ratio if you oversample a little bit. All right. Any questions about that?
The pictures that you know,
Mm-hmm.
that one has ALS.
Right. So this would what would be happening if you undersampled in this axis. So you took these samples too far apart, but along this axis you took enough samples. So you'd get this, right? But if you aliased in both dimensions, it would be a real mess, right? And then actually, just as an advanced topic, the modern scanners often have multiple coils. So, for instance, the scanner we have in Research Park has 16 coils. So each of the individual coils, if you do a reconstruction, they subsample relative to the Nyquist rate. So if you did a single reconstruction from one coil, you'll get this kind of aliased image. And then what they do is they take all the coils and they combine them together to try to disambiguate this. That's a great word, isn't it? Disambiguate, okay? Okay, to disambiguate this and to reconstruct it to try to get back that. And the advantage is that with 16 channels, with 16 coils, you can acquire, in theory, 16 times faster. In practice, you can't, because putting it back, unscrambling the egg is hard. So the unscrambling process produces some artifacts. So you need to, usually what will end up happening is if you have like 16 coils, you may only acquire 4 times faster, or, 4 times, maybe 8. I think 4 is more realistic. Okay, any questions? But it's a beautiful application of the frequency domain analysis. And we'll talk about Nyquist and sampling in a little bit. Some more detail. Okay, now I think this stuff, maybe I should have actually done this topic earlier on. But now you guys have already written some C programs, right? So Lab 1 has a C program in it, right? Okay, so there's a few things I want to go over here. How many people here? Okay, so I'm actually really feeling like a dinosaur these days. How many people here program in C? Where program in C means like you can, write a reasonable program in C. Everybody should put up your hand because you did the first lap, right? So you must know how to program in C now, okay? How many people program in C++? How many people program in Java? How many people program in MATLAB? Okay. How many people speak English? How many people breathe? I think there's some people who aren't telling the truth out there. I'm pretty sure some of you are breathing that didn't put up your hands. Okay, anyway, there's, hopefully you have, okay, I have some rules. They're basic rules for, it's like when you use, power tools like band saws and oxyacetylene torches and drill presses, there's sort of basic safety rules one must follow in order to not do anything that's really undesirable, okay? So there's some basic rules to, particularly the C programming, that I tell people to follow. I guess if you're really an expert, like the great Melendez, who used to walk across, buildings on a rope. Did you ever hear the great Melendez? Okay. Unfortunately, the great Melendez violated those rules a few too many times, okay? If you Google the guy. Okay, anyway, so it's good to follow rules because you're less likely to do something really bad, okay? And also, advice is easy to give, but, okay, I'm going to say this. I'm wasting my time, but I can't help myself, okay? You will learn, if you do a lot of programming, that it is a much better thing to very carefully write your program than to spend a lot of time debugging it, okay? Okay? And I know that it's human nature, because the first thing that happens when you want to write a program is you sit down and you go, okay, you want to go right to the keyboard and you want to start typing, okay? Because you figure, you've got all that energy. And I don't know how many times I've had students who I sent off, they said, okay, you need to implement this algorithm. and they come back, the day later, and they go, I got the whole thing written. I wrote the whole thing, okay? It's all done. I just got some debugging to do, okay? And then I talk to them in a month, and they go, well, I'm almost there. I'm still working on debugging, okay? And then, the problem is I can meet them 3 years later, and they'll still be debugging it, okay? Because once you write a very bad piece of code, you will spend the rest of your life debugging it. It's much better to have spent a week or two writing the code very carefully and designing the architecture of the code and figuring out what are the inputs and what are the outputs going to be. And then the ideal case is you spent 2 weeks writing the code and you debug it in a day. Because it's highly structured then, and now it's very easy to debug. Once you put a really horrible bug into your code, okay? It's like, it's beyond horrible, okay? Because getting it out can be just impossible. And one of the worst bugs you can possibly put in your code, okay, is some kind of a memory allocation bug. Because you'll spend the rest of your life, you may as well just get the code and delete it and start all over again, okay? Trying to find the bug. There are tools for finding the errors, but it's just horrible. It's horrible beyond belief, okay? It's like if they made a movie, they couldn't show it to minors because it would be too horrible to watch, okay? So I don't know how to convey to you that it's just very, very, very important that when you write programs to follow the rules and be very careful. So the main things I'm not an advanced programmer because I don't know Java and I don't know C++ because I'm too old now to learn them, okay? But the problem is it's like programming is like playing the piano, and I don't have enough time to play the piano right now anymore, okay? So I'll probably have to resign myself to really never learning those languages well. But I think some of the things I'm going to teach you transcend the specific language. Okay, first of all, I use strict ANSI C because if you use a stricter version of the language, it's less likely that you're going to do some egregiously horrible thing, okay? It's like leaving the blade guard on a circular saw, right? It makes sure, it restricts you a little bit with the blade guard there, but you better be really good if you're going to disable the safety feature, okay? Okay, so leave the safety features on, okay? Never use global variables. Yes, global programs will accommodate global variables, and they seem to make it easier to write the code. But you know what? Unless you are an advanced power tool user, don't go there, okay? Believe me, it's just going to make your life miserable because what will happen is that someday, long after you've forgotten that was a global variable, it will add a programming bug that you will spend 2 months trying to remove, okay? Because the thing is about global variables is they hide the inputs and outputs from subroutines. When you're looking at a subroutine and you say, x equals f of y, okay, and you call that subroutine, your assumption is that if y is the same, x should be the same. But if you have global variables, you can call this function with the same y and get a different x. And you'll go, the computer's broken, okay? But the computer's not broken, you're broken, okay? Okay, now, fix all compiler warnings. Yeah, I know that we all want to get done and go home so we can eat ice cream and watch Monk, okay? Or whatever you guys watch on TV. But you know what? It's better, Netflix or whatever. Okay, but it's clear all the compiler warnings, because sometimes you'll get a warning, you'll say, gosh, the compiler is really stupid. What is it giving me a warning about that for? And then you'll find, sure enough, it was right. Because you were calling some subroutine with the wrong variable, You were giving it, like, the amount of cheese in Wisconsin, and it was expecting, like, the distance to the sun, okay? So you're going to get some crazy output that's nonsensical, okay? And then the other thing is that I prototype all the subroutines. This is because if you prototype the subroutines, C will allow you to write programs without prototyping them. But if you prototype them, the compiler knows what the inputs are supposed to be and what the outputs should be, so it can account for that and check to make sure you're not doing something stupid. And the thing about it is that when you're doing something stupid, usually you're absolutely convinced that it's right. And you look right at the line of code that's wrong, and you say, well, that's obviously right, and it's completely wrong, okay? So you've got to, especially if you're me, I'm really bad about this stuff. I'm almost out of time, but the other thing I want to talk about is, and I think next time I'll talk briefly about is memory allocation. Memory allocation is pretty fundamental to programming, and I think it's something you can learn that translates across a number of programming languages. So good. But remember, program carefully.